In this video, we're going to review some trigonometry concepts that we're going to need throughout our calculus course. So the first thing we want to review is radian measure for angles. That's normally the measure that we're going to use for angles in this course. So for radian measure, if we're given the unit circle, which we have represented down here in this graphic, so this arc is a part of the unit circle. Notice that the radius of the circle is 1 that we have labeled here. Now we have an angle represented here, and that angle is s radians. Now what does that number s represent? Well, that s actually represents the distance along the outer edge of the unit circle from the point 1, 0 on the x-axis to the terminal side of the angle on the unit circle. So that's what radian measure represents. An angle in radians is simply the distance along the outer edge of the unit circle. Now if our angle is measured clockwise, so if we have an angle that would look like this, so if this is our angle theta right here, and this would be the unit circle right here, then this distance could actually be a negative number, and the absolute value of that number would be the distance along the outer edge of the unit circle from 1, 0 to the terminal side of the angle on the unit circle. So the s in radians can be a negative number if the angle is measured in a clockwise fashion. Now let's consider the correspondence between radians and degrees. So first of all, recall that the area of a circle of radius r is pi r squared. And the circumference of a circle is 2 pi r, or pi times diameter. So for the unit circle with a radius of 1, the circumference is 2 pi. So because of this, we have the following correspondence between degree measure and radian measure for angles. So 360 degrees corresponds to 2 pi radians. And we have a graphic down here illustrating that. So right here we have the unit circle drawn. And so the distance around the outer edge of the unit circle, going all the way around like this, the distance around the outer edge of the unit circle would be 2 pi. And so we see that that would correspond to a degree measure of 360 degrees. And because of that, we have the other correspondences here. We have that 30 degrees is pi over 6, 45 is pi over 4, 60 degrees is pi over 3 radians, 90 degrees is pi over 2 radians, 180 is pi, and 270 is 3/2 pi radians. For example, let's consider 90 degrees. That's a very common angle. So if we look at our graphic here, 90 degrees would be this right angle right here. And so in radian measure, that would be the distance along the outer edge of the unit circle from 1, 0 up to this point, which is 0, 1. And so the distance around the entire unit circle all the way around is 2 pi. And we see that this represents 1/4 of that distance. So if we take 2 pi over 4, we get pi over 2. So that's the distance from here to here, pi over 2. And so we see that pi over 2 radians corresponds to 90 degrees. And by similar reasoning, we have the other correspondences. Now you might also see a graphic like this from time to time. You'll see this in many calculus and trigonometry books. So here we have a unit circle representation here, and you see it has listed here the correspondence between degree measure and radian measure for some common angles. For example, pi over 6 corresponds to 30 degrees, pi over 4 to 45, pi over 3 to 60, and so on. And you also have these points labeled around the outer edge of the unit circle. The first point here is root 3 over 2 comma 1/2. The second one corresponding to pi over 4 radians is root 2 over 2 comma root 2 over 2. We'll use these later on to define the trigonometric functions at the common angles, like pi over 6, pi over 4, pi over 3, and so on. So these will be used in some definitions for the trigonometric functions, as we'll see later on. Now let's recall the conversion equations for degrees to radians and radians to degrees. So to convert an angle from degrees to radians, you simply multiply by pi over 180. And to convert an angle in radians to degrees, you just multiply by 180 over pi. So for example, convert 30 degrees to radian measure. Well, you just have to multiply 30 by pi over 180. And so we would get and now 30 divided by 180 30 over 180 is 1/6, and so we get pi over 6, and that's radians. To convert 5/6 pi radians to degrees, you would multiply 5 pi over 6 times 180 over pi. And so we see the pi's cancel here, and we end up with, and now that would be in degrees. And if you evaluate 900 divided by 6, that's going to be 150 degrees. So that's how we can convert degrees to radians and radians to degrees, simply by multiplying by pi over 180 or 180 over pi. From time to time we'll need to calculate arc length. So down here we have a graphic. If we're given a circle of radius r, so right here's our circle of radius r, and suppose that we want to know the distance along this part of the circle of radius r, the length of that arc. Well, it's simply going to be this. It's simply going to be the radius of your circle, r, times the angle theta. That's the one advantage of using radian measure, is that we can very easily calculate arc length. Our arc length is simply going to be the radius of the circle times your angle theta. Now that's as long as theta is in radian measure. Theta must be in radian measure to do that. So for example, suppose that the second hand of a clock is 5 inches long. Let's find the distance from that the tip of the second hand moves as it moves from the 1 to 3 position on the clock. So we want to find this distance along the outer edge of the clock. So as our second hand moves from the 1 position down to the 3 position, we want to find this distance along the outer edge of the circle of radius 5. So we need to find that distance s. Well, this angle, we have to find out what is that angle theta. Well, if we put the number 2 in here for the clock, we can easily see that this angle is going to be 60 degrees, or 1/6 of pi over 2. For example, if we put this in here, you see the angle from the 3 here up to the 1, that's going to be 2/3 of pi over 2. Pi over 2 being the right angle here. And so that is simply pi over 3, or 60 degrees. Now we don't want to use the 60 degrees in our calculations. It's just oftentimes it's easier for us to visualize degree measure than radian measure. But we want to use the pi over 3 in our calculations. So now the arc length S, that's going to be r times theta, and so that's going to be 5 inches times pi over 3, or 5/3 pi inches. And if we just evaluate that on our calculator, we get approximately 5.24 inches. So that represents the distance from here to here along that circle of radius 5. So that's how far the tip of the second hand moves as it moves from the 1 to the 3 position. Now let's take a look at this example. So suppose the second hand on a clock once again is 5 inches long. We want to find the area now swept out by the second hand as it moves from the 1 to the 6 position. So let's draw a diagram here to represent what we want to try to find. So here we have a diagram representing what we want to find. So this is the second hand right here, and it moves from 1 to 6. So what we want to do is find the area of this shaded region. So that's what we want to find. Well, so what we need to do is find the fractional part that the shaded region is of the entire circle of radius 5. So note that for a circle of radius 5, the total area is going to be pi times 5 squared, or 25 pi. Now that's the area of the entire circle of radius 5. We need to find what fractional part this is of the circle of radius 5. Well, let's take note, what is this angle right here? Let's label that angle as theta. Well, we see that that angle theta is, well, it's going to be pi over 2 plus, and the angle from here to here is going to be pi over 3. We had that pictured up here earlier. So theta is going to be pi over 2 plus pi over 3. And just simplifying this, we're finding a common denominator, or cross multiplying. 3 times pi plus 2 times pi divided by 2 times 3. I'll write that out. That's going to be 5/6 pi. Okay, so now the fractional part that the shaded region is of the entire circle is going to be 5/6 pi divided by 2 pi. And so that equates out to, let's see, the pi's will cancel here, and so we'll get 5/12. So that 5/12 represents what fractional part the shaded region here is of the entire circle of radius 5, and therefore our area that is swept out is going to be 5/12 times the area of the entire circle, which is 25 pi, and that is going to be approximately 32.72, and that would be in square inches. And that concludes our discussion of radian and degree measure for angles.